I'll come back to our Laplace transforms. So last time we discussed a Laplace transform. I then remind you, so we had a function f, function of t, and to that we would associate the Laplace transform, capital F, in function of s. It's good to give it different names, the variables, because the link, of course, is this one, where we mix the variables. Sorry. So, and to keep the variables to not get confused, we keep writing t and s. And so this is what we have to do. It's this integral, but it's a definite integral, and it's an improper it's an improper integral. Sorry, that's what I should have said. Okay, and so we sometimes call this also. Let me use the. I used this one in the previous lecture, this kind of L, but it is more common to use a fractional, this kind of curly L. So I'm gonna perhaps write curly L now, although I'm not going to use that too much, this notation. And then we have seen a special case. We calculated various cases, and I remind you a little bit of what we had. We had a small table, if you want. We show that if you have an nth power, that the Laplace transform of this nth power becomes something perhaps a little bit surprising, is this n plus 1 power in the denominator. Okay, and there's an n factorial on top. That is, so there's some things are happening there. Then we also saw this of sine and cosine. Again, they are slightly different, so they're tables, so you can always refer to the tables to do this. That's allowed. So in this type of problems, you can always go back to these tables. So the difference between the sine and the cosine is in the sine, the denominator is a constant, the frequency, and in the cosine case, it is actually the variable s. Okay, and then another case that was important was the case e a to the t, and that corresponded to 1 over, for instance, this particular s minus a. But this perhaps is what we should, we should more think of this as a result of shifting. And so this shifting can be applied to all these cases. What that means is that if, for instance, if I multiply this with e a to the t, the difference is that s is replaced by s minus a. So again, it's kind of subtracting again. It's a little bit like what we did with centers. Okay, so that's the result of, on the left-hand side, multiplying, and the right-hand side, it's a change of variables, if you want. Instead of s, we have now s minus a. And this is true for the sine and for any function. This is the shifting property, the shifting theorem. So in some sense, you do not need to memorize or have these tables. So basically, these three here really form these three that I wrote down are the basis of everything that we're going to do today. Notice, by the way, that I don't think we have calculated anything else. They all are rational functions, the Laplace transforms. Although, if we take here on the left-hand side, the original functions, there are exponentials, there are trigonometrics. There are certain things that we have not discussed. We don't have a full the full complement of all the functions that we can deal with, and we're going to focus on basically. So let me box this here. This is basically everything that we're going to work with. Okay, so this is everything that we really need. So now the first thing you could ask is, okay, so I take, and of course there are other rules, right? An important rule is that if you take a linear combination, then you're going to get, so for instance, if I want to find the Laplace transform, let me write it now, this as 3 plus 5t plus 7t squared, Well, that is 3 times the Laplace transform of 1 plus 5 times the Laplace transform of t plus 7 times the Laplace transform of t squared. This is what in linear algebra is called linear function, linear transformation. So it goes through like integrals, but of course each of these things are now whatever they are, right? L of 1. This is the special case. Perhaps it is good to mark it here. Yeah. Okay. Let me make my box a little bit bigger. So t corresponds to 1 over s. 1 corresponds to 1. T corresponds to 1 over s squared, right? Okay. So 1 corresponds to 1 over s. That is perhaps the weirdest of all. That's because you always think, oh, 1, nothing happens where. But even with 1, something happens, okay? So this would be 3 over s plus 5 over, that's now t, that is 1 over s squared, plus 7, what is this, s cubed, but times 2 factorial here on top. Don't forget the 2 factorial, so that would be a 2 there. So this would be 3s plus 5s squared plus 14s cubed. Okay, and again, this is, as I promised, a rational function. Now, normally, we would put this on a common denominator, s cubed. So this would be 3s squared plus 5s plus 14 over s cubed, if you want to write it nicely. Okay. Sorry. So now the question is, okay, if I start with something here, and I get a Laplace transform, is it possible that I start from something else and I get the same Laplace transform? And the answer is no, at least not with the functions that we are dealing with. So this means that the Laplace transform is unique. And or another way to say this is that the Laplace transform that transforms functions into other functions is an invertible process. That's, well, there are two things to say. First of all, is it true that every function is the Laplace transform of another function? That's also something that is not obvious, and we're not going to address this. So for us, basically, let's focus on the case that we're interested. We are going to claim that, or we're going to just accept that whenever we have a rational function like this, that this comes from every rational function is a Laplace transform of a unique function, and our goal is to find that unique function. Okay. So in other words, what we have to do is this was the direct road. We have to now do the indirect road. But if you think about it, this is not so hard. Let's do this in this very particular case, which is very easy, but we'll do a little bit. So suppose we started with this one. Okay. Now in this form, it is it doesn't appear in the tables in this form. Okay. But we realize that if we write it, if we divide everything by s and write it this way, that we now recognize from our tables, we have a 1 over s, a 1 over s squared, and 1 over s cubed. They are in the tables. Here's the 1 over s, this, and these two, I mean, this formula contains all the 1 over s to a certain power. So we have each of these, and we have just these coefficients. We know that these can, so in other words, from here, we can go to there. Okay, because 1 over s is the Laplace transform of this. 1 over s squared, the Laplace transform of this guy. 1 over 2 factorial over s cubed is a Laplace transform of t squared. So we can go to this direction, to this formula, we can write down. And once we have written this down, we know that we can bring everything inside here, and we find the function. Okay, so that's the argument that we're going to do. Let's start with a simple example. So yeah, I'm going to take a simpler example. The book, we'll do the more complicated ones later. Let's see here. Is this a good example? Yeah, let's do this one here. So what is the inverse? Okay, sorry, the notation would be sometimes, so because it is an inverse, right? We invert the Laplace transform. One can write this thing. So how do you write this information? Either we write it this way, this one over this double arrow notation, right? So this says that the left-hand side and the right hand is from the left hand side you get to the right hand side by doing a Laplace transform, and the double arrow now makes more sense. It says it's kind of a unique process. You can go back, okay? Or we also can write that the inverse Laplace transform of 3s squared plus 5s plus 14 over s cubed is 3 plus 5t plus 7t squared. So we use just this notation, L to the power minus 1. It doesn't mean reciprocal, but okay, the power negative 1 is sometimes a bit confusing, and it's the same power negative 1 as we use in tangent inverse or cosine inverse, arc sine and arc tangent and arc cosine. It means the inverse function, okay? But that's just notation. The more thing is the calculation part. So let's look at an example here. I'll do the example. So what is the inverse Laplace transform of 3s plus 2 over s squared minus 3s plus 2? And you'll see everything what we're going to do here today is, because we're dealing with rational function, is partial fractions. We have encountered them already a couple of times, but now we're going to have to use them seriously. So it's a little bit of review of partial fractions. And so I remind you what is the statement here. That is, if we have a rational function, so if we have something px over qx, so p and q are polynomials, then we can write this as simpler things. Namely, in the denominator we have some x minus a to a perhaps certain power, okay, or, so there are a lot of these guys, I'm just writing one of them, or another instance is what is called a quadratic irreducible. So something of the form, any quadratic irreducible is of this form, and this is important for us, so I'm going to write it like that, x plus a squared plus b. So these are quadratic irreducibles. And what is on top here? Well, on top here, if we have a linear form like that to a certain power, there is just going to be a constant. On top of this thing will be something of the form x, a linear polynomial, but very often we factor it again in powers of x plus a. This is now, we are much more used to these powers of x minus x plus. Yeah, I don't know why, sorry. Let me rewrite this a little bit because it's a little bit messy. So I'm going to write it again, and so if we have a rational function, so p and q are polynomials, and we have a rational function, then this is a sum of two types of things. We can have x minus, and let me now write perhaps x0 to be a little bit more in the same spirit of power series from chapter 7, to a certain power here, n, and on top we would have a coefficient, okay? Or the other form is that in the bottom we get what is called a quadratic irreducible, which looks something like this, and then on top we would again take a polynomial of degree 1, but we again write it as a polynomial in x minus this x0. Okay, and so these x0s, where they come from, so the x0s, sorry, not, yeah, I should be careful. Now, let me not say this, where these x0s come from. So what we're saying is, partial fraction says you can always write it as a sum of this and something of this form, terms of this type, plus terms of that type. So there's two types here, and this type is kind of a bit, can be separated in two special cases, namely that n is 1, that's the easy case, and that n is of higher order. That's a more complicated case, okay? And but there is one important restriction, and this is that the degree of p has to be less than the degree of q in this in this rational function. Now that's not always the case. Sometimes you have a polynomial, sorry, on top is degree 3 and on the bottom is degree 2. What do you do then? If this is not the case, you do, so if not the degree p less than degree q, first do long division. Okay. Now we are not going to see this because, in fact, I don't know whether you noticed, but the inverse Laplace transform of S or even of 1 we don't have yet. In our tables, if you search for our tables, you see there is actually really nothing there, at least not in the tables that, let me, in the first page of these tables, there is no constant. What is the Laplace transform of a constant? What is the Laplace transform? The Laplace transform of a constant we know, that's that. I meant the inverse. So you see, these are all really true rational functions. But what is the inverse Laplace transform of a variable, or the inverse Laplace transform of a constant, right? So yes, certain things do not have Laplace transforms, and so we have to be careful with that, okay? All right, so we're never going to be in this case, so therefore I'm going to put this between parentheses, but I just want to point out that this is something that one should pay attention to, but this will not happen to us, luckily. So, okay, going back to my example, it's here, the example. So what we need to do is, we have to write this into partial fractions. So, the method of partial fractions. And I urge you to go back to your calculus book to see how this goes, because there are different steps here. We will do one of each, but I'm just going to do the method. I'm not going to explain the whole method again to you. Although there's one thing let's do this on this particular example here. So 3s plus 2 over s squared minus 3s plus 2. So the first thing we have to do, step 1, is to factor the denominator. That is always part of the calculation. So the denominator, not the numerator. Numerator, the only thing that we need to know about the numerator is that the degree is less, and that's the case here, right? It's degree 1, and the bottom is degree 2. Okay, so we have to factor so s squared minus 3s plus 2. We need two numbers that multiply to 2 and add up to -3. Well, that is -2 and -1. So we see that the roots are s is 1 and s is 2. Now the roots are also important in some of the methods here. So okay. Then we know that step 2 is, we know that this has to be of the form, as I said, we have this s minus 1 and this s minus 2 here. And on top we have some coefficients. So these are these special cases. This was the case on the top case here. And we will have exactly one of these for each of the roots that we have. Okay? Now this is a special case, is that the case where we have two different roots. Or we'll see even, it doesn't always have to be quadratic here. So where we have all distinct roots. In the terminology that we introduced a little bit earlier, all these roots have multiplicity 1. Okay, we will deal with what happens if the multiplicity is higher. So we know that we can always write this in this case. And then the next step is to find a and b. And there are many methods here. The most obvious method is to just work it out by comparing coefficients or by plugging in roots, which we have done a couple of times. So we want to multiply both sides with s minus 1 times s minus 2. So s minus 1 times s minus 2, s minus 1 times s minus 2. We do this, then this cancels. I'm looking at this in this equality, right? So like this way. Okay, so here the s minus 1 cancels, here the s minus 2 cancels. So I find that on the left hand side I have 3s plus 2. The numerator is equal to a times s minus 2 plus b times s minus 1. And then step 4 is we plug in the roots. So that means I plug in s equals 2. Now if I plug in s equals 2, notice that this term disappears, right? And so what we're left with is, on the left hand side, if I plug in 2, I get 6 plus 2. 6 plus 2. On the right hand side, I get a times 0 plus b. So I see that b is 8. If I plug in s equals 1, then I get 3 plus 2. Let me write it like this. And then I get a 1 minus 2, that's minus 1, plus b times 0. So again, we can find that A is minus 5. So the conclusion is that we have 3s plus 2 over s squared minus 3s plus 2 is equal to minus 5 times s minus 1 plus 8 times s minus 2. And I remind you that, okay, I chose this order, first s minus 1 and s minus 2, but the order is irrelevant. Okay, if you write it in a different order, eventually you're going to get the same polynomial, perhaps written in same sum of fractions, perhaps written in different order, but that's it. It's only the order that is different. Okay, so this is where we are. S plus 2, where was my s plus 2 come? S minus 2, of course. Yeah, both were, did I? No, okay, I just copied that wrong. Okay. S minus 2. So now, going back to our thing, now let's take the inverse transform of this fraction that we are interested in, right? That's the whole point. So we said, okay, we can split this as minus 5 times the inverse Laplace transform s minus 1 plus 8 times the inverse Laplace transform, inverse Laplace transform of 1 over s minus 2. Yeah, we'll write it this way. So what are these? Well, in the table that I created, I had only, in the left-hand side, I had only powers of s. What do we do? If it's the power of s minus something or s plus something? Well, that is done by the shifting, okay? And that is done by having an e to the at in front of it. So in this particular case, it's just this one. It's just this formula that we're going to use. We'll see later in higher order what we need to do. But okay, so this means that we just have, this is minus 5 times e to the 1t. So here is a is 1. And here plus 8 times e to the 2t. Okay, that's it. That's all we need to do. So be careful with the signs here. So here, this is, I know sometimes in our formulas we have a minus sign with the at, especially in the definition, but here it is a plus sign. So this is a coefficient when you write it as s minus something. Okay, so we'll see later what to do with this thing. So okay, that's the inverse Laplace transform. Now, there is a shortcut. So a shortcut due to a Heaviside. Heaviside is a name of a mathematician. Heaviside's method. But it is very important to note, applies only, and I'm going to stress this, if all roots have multiplicity 1. Multiplicity 1. So that was the case that we have. What do we do then? Well, what you do then is you take this fraction here. Let's for the moment just call this. No, sorry, I should not write the fraction. So we want to calculate this. Let's look at 3s plus 2. Now, the first thing we do need to factor, because we need to know whether the multiplicity is 1 or not, right? So we write it as s minus 1 times s minus 2, okay? And now we know it is the form a times s minus 1 plus b times s minus 2. And the question is, how do you find a? Well, you find a as follows. You take 3s plus 2 over s minus 1, s minus 2, and you factor out, so that in red, this s minus 1 here. A is on top of s minus 1, you factor that out. And then you take the limit, well, there's not a limit, you evaluate at s equals 1, the root. Okay, so this 1 is the root that corresponds to this factor. And that's the factor that you have cancelled out of this expression. Okay, the original expression, you factor away, that's why you need a factor denominator. You scratch out the that one factor, and now you plug in. Let's see what happens if I plug in. On top I get 3 plus 2, that's 5, and in the bottom I get 1 minus 2, that's minus 1, so negative 5, and that's exactly what we had, right? This is my A. Yeah, here we see. And the same for B. So B is equal to 3s plus 2, s minus 1, s minus 2, but you cancel the s minus 2 and you plug in s equals 2, and then you get 3 times 2 plus 2, that is 6 plus is 8 over 2 minus 1 over 1, that is 8, and that's exactly what we found. Okay, so let me do this on another example here. I have this one. So we have s cubed minus 4s squared plus 6s plus 17 divided by s times s minus 1 times s minus 2 times s plus 1. Okay, so here for us, nice of them, they have factored this. Okay, so it is factored, and we see it all different factors. That's what it means to have all multiplicity 1. So Heaviside method applies. So we know, so I'm going to find the inverse Laplace transform of this rational function using Heaviside's method. So I know that we have a over s plus b over s minus 1 plus c over s minus 2 plus d over s plus 1. You see that if you would have to do the original method, it's still a little bit of ugly calculations, right? And you could get messy and you could make mistakes. So here what we do now is, what is a? So I'll do the calculation of each of them, but I'll cheat a little bit. I'll do it by erasing. So here I'm going to write down my function, the original function, s cubed minus 4s squared plus 6s plus 17 over s times s minus 1 times s minus 2 times s plus 1. And now I'll calculate a. So what do I do if I calculate a? Well, a is on top of s, so I scratch out s, and s equals 0, that corresponds to s equals, well, that corresponds to s equals 0. Okay, so I plug in 0, and what I get? I find that a is equal to, well, 0, everything that's 17 on top, and in the bottom I get minus 1 times minus 2 times 1, so I get minus 17 over 2. That is a. Okay, so as I said, I'm going to do this by erasing, and I'm going to put each of my calculations already ready. This is minus 17 over 2. Now b. So this is where the sheet, where I make my life easy by erasing everything. And I say, okay, now I'll go for b. So what happens in b? Well, b is on top of s minus 1, so that's the guy that has to go. And now I have to put s equal to 1. Okay. Of course, I have to scratch the s minus 1, because otherwise if I plug in n1, I get a 0 in the denominator, right? So, but what I get then is on top, I get 1 minus 4 plus 6 plus 17 divided by 1 times minus 1 times 2. And what does that mean? On top, I get 23, 24 minus 4 is 20, divided minus 2 is minus 10. Okay, so b has become minus 10. So minus 10. So C, let's do the calculation for C. Okay, so okay, so what happens with C? I hope by now you see what we need to do, right? We cancel what C is on top of S minus 2. Always check what is on top of, right? So, because you might have chosen, I mean, there's no reason to choose this order just because they wrote it that order, but so C by 2, and what you plug in? S is 2, right? Okay, so let's do that. So we get 8 minus 16 plus 12 plus 17 divided over 2 times 1 times 3. Of course, you never can get 0 in the denominator, because otherwise you cancel the wrong thing. So that's, what does that mean? On top, minus 8, 4, so 21 over 5, over 6. I thought this was 21. Oh yeah, 21 over 6. So if I divide the common factor 3, 7 halves, right? So, Jesus. Why does it do that? 7 halves. Okay, and then finally D again. Oh yeah, so let me write it up here. So this is 7/2. So now I can erase it. Of course, you can on a test you cannot do this, right? You have to show each of the calculations separately. So now D. This time I have to factor out this one. What do you have to plug in here? S equals 1? No, S equals -1. Right? It's exactly the guy that makes that factor 0. Okay, if I plug in -1, I get the cube of -1 is -1. The square of -1 is +1, so -4, -6 plus 17 over -1 times -2 times -3. And on top I get 4, what is that here? 10, 11, 6. And in the bottom I get -6, so I get -1. Okay? So D is -1. Okay, so I can now already write down the inverse Laplace transform. So inverse Laplace transform, we have these coefficients, -17 over 2, and then we have 1 over S. We know that 1 over S corresponds to what? Well, let's go back. 1 over S just corresponds to 1. Okay, so this is just 1. I mean, it's strange, but it is what it happens. So it's just a 1 here. Then the next factor, that is -10, and we have to do the inverse Laplace transform of 1 over S minus 1. But that's the shift of of 1, if you want, by this guy. Oh, sorry, I didn't want to circle this. Okay, so and so we're shifting it. This is a shift by 1, so this is e to the t, and then plus 7/2. What is the shift here? 2, so 2t. And then finally, -1. What is the shift here? Be careful. The shift here is -1, right? So this is S minus -1. So we have minus t here. And this is our original function of which we took the okay. Okay. So what when you have a multiple factors, and it can be a little bit annoying then. So in multiple factors, you cannot do this Heaviside method. So you really have to work out the details of it. Now that can be a little bit annoying, and I don't want to make the movie too long. So I'm going to leave that to you. Although I'm going to do one special case of that, where it actually becomes again easier. So here is the case that I want to do. So let's look at this case. Suppose we have the inverse Laplace transform of s squared minus 5s plus 7 over s plus 2 cube. Okay. So this is a special case of a multiple root. So in general, of course, we could have something like s plus 1 times s plus 2 cube times s plus 4 square. So if this is, suppose this would be the denominator, just to fix our notation again, this would be multiplicity 1, this would be multiplicity 3, this would be multiplicity 2. And so what we need in this in general case, just let's point out what we need here. So if this is the denominator, let's say there's something on top here, doesn't matter what it is. If this is our denominator, then we know that the partial fraction is going to be s plus 1. Now, what about the root of multiplicity 3? Well, you say, oh, s plus 2 cube, right? Yes, but you also need the lower powers. So not only s plus 2, but s plus 2 cube, but also s plus 2 squared and s plus 2. So this contributes actually with 3 terms. Multiplicity 3 will have 3 terms that contribute. And what about multiplicity 2? Well, okay, you have s plus 4 squared and also s plus 4. So this would be an E and an F. So 1, 2, 3, 4, 5, 6 undeterminates. How many of these undeterminates will there be? Always equal to the degree of this polynomial. Okay, so that's why we cannot leave these terms out here, because then there would be way too little undetermined coefficients. Okay, so what a multiplicity does is it says, okay, you have to take that linear factor to that power and everything that is lower than that power. Okay, so particularly in this particular case, since there is no other roots, there's only this one single guy, no other factors, I mean. So this, in this particular case, this means that there would be well, it would be exactly these three terms, right? It must be something of this form. Now, in order to get to that form, in this particular case, so I remind you, this I cannot do what I'm going to do on this more general case, and that's why I'm kind of for now skipping it. I'm leaving that to a homework problem. So in that case, so let me go here. What I'm going to do is I'm going to write the top as a polynomial in s plus 2. From power series, we know that this is actually something that makes sense to do. So that remember, the way to do that is you write s as s plus 2 minus 2 and plug in. So let's do this. We get s plus 2 minus 2 squared minus 5 times s plus 2 minus 2 plus 7. Okay, what is that? Expand this. Remember, s plus 2 is now something that we cannot touch. We don't expand that. So s plus 2 squared, double product formula, minus 4s plus 2 plus 4 minus 5 times s plus 2 plus 10 plus 7. So this is equal to s plus 2 squared. We have a minus 4 and minus 1, minus 9s plus 2. And then the constant is 4 plus 10 plus 7 is 21. Okay? So that's what we get. So why do we do that? So we have now written it in the polynomial that we want. So let's now write the fraction again. So we get, but now using the new form as a polynomial s plus 2. And in the bottom we get s plus 2 cube. Well, now we just do the division, each term separately. Remember, this was exactly what we did all the way in the beginning, right? Instead of s plus 2, we had just s here. That was more obvious for us to do that, but now that we have written it in this form, it also becomes obvious to do this, right? So we divide each term by s plus 2 cube. I'll write it up one more time just to see that you see what happens. And so you get this here, and you'll get 21s plus 2 cube. Okay, and so now the cancellations that we are expecting, or I mean that we have, this cancels completely, and there's a 1. This cancels, and there comes a 2, and that of course there's no cancellation there. So we get this is equal to 1 over s plus 2 minus 9 times s plus 2 squared plus 21 s plus 2 cube. Now, this is the fraction. So what is the inverse Laplace transform of this thing? Well, remember, these powers, powers here correspond to the Laplace transforms of powers of t, but with difference in degree, right? And there's also this factorial that we have to think about. Now that is if the variable is s, if the variable is, or in the denominator the factor is s minus a, that comes from a shift. So what is the shift here? So the shift from the shift theory is we have that a is negative 2, right? Because it's s minus 2, that's s plus 2. So each of these terms is gonna have an e minus 2t, okay? And the first one, since it's all going to have the same term, but let me write it. So what's the first one? Well, that's just coming from 1, right? Remember, it's so in general we have, let me write it up here, the Laplace transform of Tn is 1 over s to the power n plus 1 and factorial here. Let me write it that way. So in other words, whatever power you have here, the inverse will have a power less. This is power 1, so the inverse will be just a constant. This will be power 2, so the inverse will be t. So we get, and this was a 9, so, right? So this is minus 9t, e to the minus 2t, and this will be plus 21. Now we have to be careful here, because it's a cube here. So let me write down what we're expecting. We're expecting this to be t squared, e to the minus 2t, but there's a factorial, so we have to divide by that factorial, right? So we can bring the factorial to the other side. So what I mean to say is, so L of t squared is 2 factorial over s cubed, which is just 2 over s cubed. Let's not make it too fancy. So this means that a half L of t squared is 1 over s cubed. So if I want to do the inverse Laplace transform of 1s cubed, that is a half is a half t squared. That's what I meant to say. So we have to compensate by that factorial again. So that's what we get here. 2 squared, of course, is just 2. Okay? And so we can now, as I said, since this all has the same term here, which is almost a sin not to do that, right? Factor it out. So you get 1 minus 9t plus 21t squared over 2. And there you have your inverse Laplace. Now, okay. So far we have been dealing with somehow easier case in where we can factor the partial fractions here. No, those are my partial fractions. Here. Perhaps I should box this too a little bit. So these are the partial fractions here. So far we are dealing with a case where we have all these factors here, simple linear factors. But this is a bit different thing. This is what we call a quadratic irreducible. And so let me give you a simple example of that first. So this time I'm going to have to do a little bit of calculation. So let me see here. I'm going to take the example from the book. Okay, here it is. Okay. Okay, give me a sec because I have to actually. I thought I had it written down, but I didn't. So I'm going to calculate something for you. Okay, so this is 8x squared plus 3 plus 7x plus 5. So this is. So I'm going to want to find the inverse Laplace transform of 8s squared plus 7s. 24 plus 35. 20. 35, 59. Plus 59 over s plus 5 times s squared plus 3. Okay. So, again, it's the same thing. We have to write this as partial fraction. So we start with the partial fraction part. So what does that look like? We have 8s squared plus 7s plus 59 over s plus 5 s squared plus 3. And so what I said was that this will be of the form, well, we have this s plus 5 here. That will be just a constant in front. But this guy is, we cannot factor s squared plus 3. Not at least in reals. We can factor it in the complexes, but we don't want to do that. So because this is still we work always real well, right? So s squared plus 3, sorry, that's square is a little bit. On top of this, we will have a polynomial in the same variable s, because it's kind of what I'm saying seems to be kind of silly. I'm saying, okay, write this as a polynomial in s, but this might be, instead of s, we might have, for instance, I gave an example, I think here, right? We'll see other examples, but I just want to show you what I mean here. Well, this is how the general form looks like. Okay, so the variable could be. We'll see later example what I mean. Okay, so this is how it looks like. Now, to do this, we cannot use Heaviside methods. So do not use Heaviside. Look, when I teach this in Calculus 2, I know this Heaviside method, but I do not teach it because I know people are then inclined to use it all the time, and that is wrong. Okay, you cannot use it all the time. Well, in some sense, it's clearer here that you cannot use it because what is it? What would it supposed to mean? Okay, for A you can do this, fine, But what do you do? How are you going to find b? You have to plug in. Remember, you say, okay, you cancel this thing and you plug in the root here. But there's no root. Well, there's a complex root, but we don't do that. Okay. So, so what to do here? So what we need to do is really multiply everything out. So I'm multiplying this whole thing out with the s plus 5, s squared plus 3, s plus 5, s squared plus 3, and here also, of course, s plus 5, s squared plus 3. So what we left with is 8s squared plus 7s plus 59 is equal to a s squared plus 3, the s plus 5 cancels, right? And here the quadratic cancelled, plus bs plus c s plus 5. Okay, now we can plug in the root, because we have a root, we have one root, namely coming from s plus 5, s equal to negative 5. Why? Because this will make this term disappear, which is good. So what we get is then we get 8 times 25 minus 35 plus 59 equals 28a. Okay, and this is 8 times 25 is 200. So we get 259, we get 224 is equal to 28a, and I think that is yeah, that is, sorry, yes. So that is, so a is equal to 224 divided by 28, which is actually 8. Okay, so we have a. But how do we find b and c? Well, now we have no choice than to expand and compare coefficients, or just plug in special values. So there are two methods now. So either compare coefficients by expanding, what we have done often in this course, or plug in values for s. Okay, so that's another thing we can do. So compare the coefficients. What do I mean with that? Well, expand this, we get, what do we get? A s, but we know that a is 8, so let me write that already. 8 times s squared plus 3 plus, now I have to expand this, that would be b s squared plus 5b s plus cs plus 5c, okay? And that has to be equal to 5c, yeah, this has to be equal to 8s squared plus 7s plus 59. So we look at the coefficients of s squared. The coefficient of s squared is an 8s squared and a bs squared. So 8 plus b, that has to be equal to 8. What's the coefficient? This, so let me write it a little bit clearer here. So the coefficient of s squared on the left hand side, it's not clear what the left hand side is. And the former one, it is 8 plus b. Okay, here is this one and this one, right? And this is equal to 8. So let me do it in colors. This one, this one, this one. Okay, so what is the one coefficient of s? So there is one here and there's one here. So this 5b plus c. And that has to be equal to 7. And then finally there's a constant. So the coefficient of 1, the constant if you want, right? That is 20, be careful, we have a 24 here, 8 times 3, and 5c, plus 5c, right? And that has to be equal to 59. Now, it is a bit strange here. We have 3 equations, but only 2 unknowns. So it better works. So let's see. Is this okay? Well, the first one actually tells us that b is 0. That's already nice. Okay, b is 0. If b is 0, then we see that from the second one, that c is 7. So now is the question, is this true? And this is not. Oh yeah, it is true. If I plug in c equals 7, then I get 24 plus 35 is 59. So this actually checks. If this would not check, then we made a mistake, because it has to check. So this The comparing coefficients has this little built-in thing that you can see whether you made a mistake or not. The other method is you plug in just values of s, apart from the value -5, because we have already used that. So if I plug in s equals 0, that's the most obvious choice first, then the left-hand side becomes 59, and what does the right-hand side become? Well, the b disappears, and we see that is, so if I plug in 0 here, so this will become 0, and this is 30, so get just 5c. Sorry, yeah, but also have to plug it in here, sorry. So I get 3a plus 5c, right? Don't forget there's a term, but 3 was, so a was 3, so this is 59 is 24 plus 5c, so bring this to the side, and I get 35 equals 5c, and I find that c is 7, same 7 that I found before, and then I find another one, let's say plug in s equals 1, so on the right hand side I get 8 plus 7 plus 59, and that should then be equal to a 4 times a plus b plus c times 6. Okay, this is the result of plugging in 1 in here. Now we know most of the values. So the right hand side is 15 plus 59, that is 74, equals 4a, but a was 8, so that is 32, plus 6b, which we don't know yet, plus 6c, that is 42. Okay? So we bring everything on the other side, but we see that actually 0 is 6b, and therefore b is equal to 0. Again, what we found. So there's two different ways to get to the same result. So what is the result? The result is, I'm going to cheat a little bit here, that because otherwise I'm going to make copy errors if I don't do this. Okay, so this, let me erase all this here. We don't want this anymore. So this is there. So the a was 8. So I'm going to plug this just in. And the b was 0, which is nice. And we will see with cases when this not happens, because there's something else we have to do. And then the c was, what was the c? c was 7. c was 7. So this is what we get. Okay. So let me erase this here also. What can we? How do we find this now? Let me copy this so that we don't get. I don't want to erase too much here. So I'll copy it here. So this allows us now to calculate the inverse Laplace transform. So let me just do the. I'm doing the inverse Laplace transform. The 8 of s plus 5. That is now. By this time we should know it is just power. And so this corresponds to powers together with an exponential due to the shift. The power is 1, so that corresponds, the power 1 corresponds to something of lower. If 1 over s comes from a constant, the 0 power, and 1 over s squared comes from t to the power 1, 1 over s cubed from t to the square, okay? So this is 8. Sorry, I'm writing it down here. So 8 e to the minus 5t. Why the 8? Because we have, this has degree 1, so this will have degree 0, 8 times 1 if you want. This is a shift of minus 5, this s minus 5, so e to the minus 5t. Now what is this one? Can I do the same thing? Well, first of all, what's the shift here? Well, the variable is s, so the shift will be 0, so there will be no exponential here. But what then? What then? Well, let's look what we have here. We have our tables. We haven't used these guys yet. And this is exactly where the quadratic irreducibles. The quadratic irreducibles are going to give me the two trig functions here. So far, we only have gotten the top part, right? But now, this is where they come from. Look, so we have an s squared plus omega squared, s squared plus omega squared. What's the difference? Whether it's a constant or a variable on top of it. What we have the constant, we are in the case of the constant, so we will have sine omega t. So I'll write it up here again. Where am I? So what we have here on the side, the Laplace transform of sine omega t is omega over omega squared plus s squared plus omega squared. Let me write it in the right order. S squared plus omega squared. So let's recognize what do we have here. Yeah, first of all, let me rewrite this slightly by bringing the omega to the other side, which means that 1 over omega, or if you want, I can bring the 1 over omega inside the Laplace transform, right? So let me do it that way. So this means that the Laplace transform of 1 over omega sine omega t is 1 over s squared plus omega squared. That makes it a little bit easier to see what I have to do here. So we're going to have this 7. That comes just out. And then we're going to have we have this guy. So what is omega in this case? In this case, omega is 3? No, radical 3. We always take the positive frequency here, right? Because it's this in the formula we have to have a square here. So it has to be radical 3 squared. So omega is 3. So we can now use this form. It is 1 over radical 3 sine omega radical 3t. And because it was s, there's no shift. Okay, so this is how this looks like. Okay, but what when you have a shift? So I want to do. Let's see here. I will this is. I make this my last example. Okay, so let me see this one. Yeah, okay. So the inverse Laplace transform of the following function here. Yeah, okay. I'll work it out. I thought I'm not going to work it out, but let me work it out because it's good to see this. So yeah, the function I'm looking at is this one here. Okay, it's f of s. So I want the transform of this one here. Now it's a bit weirdly written. So minus 6x squared minus 10s plus 1 over s times s squared plus 2s plus 2. Okay, let's look at this one. The book is slightly different, so I'm gonna. Okay. Sorry, plus 2 here, plus 2. Right. Make sure that I copied it right. Made slight changes, but I'm making sure that I changes are coherent. Okay. Yes. So this is it. So it's factored. Well, you say no. You can factor s squared plus 2s plus 12. Well, if you do that with the quadratic formula, you see it doesn't work. Why? Well, remember, this all comes down to the discriminant, right? The discriminant is b squared minus 4ac. So in this case, that would be 4 minus 8. You see that? Which is negative 4, which is negative. We know that there is only 2 complex conjugate roots, so no real roots. And this is exactly what it means, a quadratic irreducible. That is what that means. To be quadratic irreducible means exactly that. Okay, so what do we do with that? So a quadratic irreducible, at this we can. There's 2 things you can do, 2 stages you can work out. And in the book they work the stage immediately, but I'm going to take my time a little bit. I'm going to say, well, first of all, we know that it must look like at the s here. That's just a regular factor, so that will be that. And the other factor, we know that we're going to have. No, sorry. Okay, no, sorry. Yeah, let me say it differently, sorry. The quadratic irreducible. The first thing we need to do, let's do this, is complete the square. So we have to write this as a complete square. Now, how does this go? Remember, you take the 2 terms that contain an s, and then you take the plus 2. This, I'm rewriting this guy, right? So let me write it. So s squared plus 2s plus 2. Okay. Now it gets a bit more complicated if there's a factor in front of s squared. So for simplicity, let's assume that's not the case. And so we have s squared plus 2s. I group the 2 terms with an s in, and I add the thing that I need to add to make it this guy a perfect square. The plus 1. Where does it come from? Well, you divide this number by 2, and then you square it. That's the two steps. Now, of course, divide 2 by 2, that's 1, and squaring it is 1. So that's why it seems like there's no second step, but in general it is, right? Now, when I add a plus 1 here, well, I cannot do that. I have to compensate and subtract the 1, because this thing has to stay the same. Whatever I add, I have to subtract again. So what does this now mean? And here we have our completed square. We have an s plus 1 squared, right? This is the one that I found here, that 1. This is there's 1. If I divide it by 2, I get 1, right? And then I'm squaring it another one. That 1 is that's what we get here. It's s plus 1 squared plus 1. This whole thing is s plus 1 squared. What is this? Well, that's just 1. Sorry, there's a lot of 1s here, but they're all different, right? They come up from different cases. So, once we have done this, we're going to now write, so proposed partial fraction. So bear with me, right? It's a little bit of work here. It's going to take a little bit more time, so it's a bit longer video, but it's, yeah. What we're going to do is write this fraction here. Yeah, let me copy the fraction, because otherwise I'm going to... So I'm going to write this fraction as follows. Let's do this. Okay, so I'm going to write this fraction here, this one. I know that it can be written. The s, that's just a nice root, multiplicity 1, so there's going to be an as there. If the higher multiplicity, I would have more terms here, right? Plus, and what is on top? Well, I know that this guy, so I'm going to rewrite my denominator now. Oh, I can do that, okay. Oh, no, I cannot do that, right. So I'm going to have to scratch it out and say, well, I know that I can write it as s plus 1 squared plus 1. Why? Because it tells me, so s plus 1 squared plus 1, that instead of s, we're going to use s plus 1 as my variable. Thinking again as rewriting polynomials in different centers, right? So center is -1 here, okay? So this means I'm going to write it as not a, because a is already in use, b times s plus 1 plus c. This is how a polynomial of degree 1 in s plus 1 would look like. There's a reason I do this. Okay, so that's, once I've done this, and this has to be equal to this fraction, I do the same thing. I multiply top and bottom with, I multiply both sides with the common denominator, and I hope, I'm going to skip this, but please make sure that you verify this. The result of that will be a, when I multiply here with the denominator here, the s's will cancel and this one will survive. So s plus 1 squared plus 1. Do not expand, right? We're keeping this now in the form that we have. Plus, and also the same here. We have b s plus 1 plus c times this guy, right? That guy will still stay. The other one will be cancelled. And that is equal to minus 6x squared minus 10s plus 2. Okay. So, and again, do not expand here yet. Or I would not expand at all. So step 1, so plug in the roots. Well, we have only one root, that is s equals 0. But okay, if I plug this in, I get an a plus b plus, oh no, this s is 0. So all this whole thing, that's the whole point, right? This whole thing is gone. So there's only an a left. And that is equal to, plus a is equal to 2. Let me double check here. I want to make sure. Yeah, no. Well, okay, whatever might happen. Okay, so now the roots are finished, so plug in values for s other than 0. Because we have used it, s equals 1. Or let's do s equals -1. S equals -1. Why? Well, then all the s plus 1s are kind of disappear. At least makes it a little bit quicker to see what we have. Well, we get, if I do this here, what I get, the first one is just a. The second one, the b is gone. We get c times -1, because s is -1. equals minus 6 plus 10 plus 2, right? Minus 1 squared is 1, and then we have minus minus is plus 10. And A is 2, so actually I find C. So A is, so plug in values, but the first value that you plug in is the center. Okay, if you can, but because it might be that the center is also a root. That is not a contradiction at all. That can happen. Center and root have nothing to do with each other here. So, but here we are in the situation that the center is different from the root, so that's nice for us. This makes things life easier. 2 minus C equals, and that is 12 is 6. So we see that minus 4 is equal to C. Okay. And now finally, we now have to plug in some value, say S equals 1. So a third value that I choose. So this one, as I say, is root. This one, if I can, I use the center. And otherwise I have to plug in something. Now let's see what I plug in. If I plug in 1, then we get 2 squared plus 1, that is 5a, plus 2b plus c times 1 equals minus 6 minus 10 plus 2. Okay, that is the result of plugging in 1 in here. Now we know a lot of these guys. A is 2, so that is 10, plus 2b, and c was negative 4, minus 4, and that is equal to minus 16, minus 14. So this means, if I bring everything to the other side, 2b is equal to minus 14 minus 10 plus 4, that is minus 20, so b is equal to negative 10. Okay. Okay, so what does that mean? Okay, so let's go back to our guy. I hope I still have it, right? So this guy now looks as follows. What was A? A was 2. Is 2 over S plus minus 10 S plus 1. That's the B. And then the C here, right? And the C was negative 4 minus 4 over S plus 1 squared plus 1. That was our denominator. What do we do now? Well, now we split this. We split. It's 2s plus minus 10 s plus 1 over s plus 1 squared plus 1 minus 4 s plus 1 squared plus 1. Why do I split? Well, remember our table in the beginning. Let's see. There are two types of with a square plus with a quadratic irreducible. This is just how a quadratic irreducible looks like, at least before a shift. When we also have to do a shift, but apart from the shift, this is how this looks like. But on top you could have either a constant, which corresponds to the sign, or a variable which corresponds to the cosine. Now the variable is the same variable here, so that's why we made this to be s plus 1, because in the denominator the variable is s plus 1. So we want on top to be the variable s plus 1. So this comes from the cosine. Okay, so let's try to write everything down. In the first one, there's no shift, so there will be no e exponential. Okay, so this will be just 2, because the inverse Laplace of 1 over s is just 1. Okay, that minus 10. Now here is a shift. So in this case, there is a shift with a equals negative 1, right? Because it's s plus 1, so this s minus minus 1. So this will lead to the e minus t, and what we get then, we have the variable, I meant the point, the variable over the variable squared plus 1. So what is omega here? So omega is, well, the square root of 1, but that's luckily 1. So this therefore corresponds to the cosine omega t, which is just t here. Omega is just 1. And then finally, minus 4, what is this? I'm not going to write it out, so think about it and just convince yourself that that's what this is. Okay, so that's all the various methods that we have to do. So it's basically a lot of completing the square. There is one example that I've not worked out, and I think I'll might give a homework problem that uses that trick but basically it's all about partial fractions, and then making sure that you know exactly how to shift everything. Okay, so and here we see a little bit, this is the general forms, right? So so we could have something, we have now seen every particular form that can happen. So and the result will be either an exponential times a power of t. Well, here it's constant power, and there's no exponential, but we have seen examples, right? Where was this here? This one here, right? An exponential times powers of t, or an exponential with cosines and sines. That's what we have here. Exponentials with cosines and sines, and the exponentials might or might not be there depending on shifts. All right.